अब दिख रहा है.
स्टार्ट करोगे?
हाँ.
Hello everyone. So as we giving an introductory talk on Neumann algebras, and this is an introductory talk, so please feel free to interrupt if you have any questions. Okay, so I'll be first giving motivation on why we will define. I mean, why to define these Neumann algebras. Then I will go through the basic theory, few examples, and then I'll go through the so-called theory of projections, and then we'll briefly look at the Neumann algebras for Hessian Neumann algebras. So this is the plan, and I plan to spend quite some time on the motivation part. So before starting, here is the notation that we use. So B of H is used for the space of bounded linear operators on the Hilbert space H, and we'll use small English letters to denote its elements. And then we'll use these Greek letters xi, eta, and zeta to denote vectors in the Hilbert space. And then if we have a C-star algebra, so what that is, we'll come to in a bit. But if we have a C-star algebra A, then this A is subscript SA, and A plus will denote the self-adjoint and positive elements respectively. And now we will see the definition of a von Neumann algebra. So a von Neumann algebra is a star subalgebra of B of H, which is closed under the topology of quantized elements. So that means whenever we have a net in this M and given any operator x satisfying xi xi converges to xi for any vector xi, we should also have that this x is 0. So this theory was developed by von Neumann and his student Murray between 1936 and 1949 to study quantum mechanics. And this has connections with various areas of mathematics. For example, Paul introduced something called non-commutative geometry, and Jones introduced the Jones polynomial, which revolutionized the field of knot theory in topology. I hope I am saying it correctly. For their work, Jones and Cohn won fields in and also we have something called free probability. So it is related. It is a kind of a generalization of probability, and it was initiated by Walters. So let's go into the subject matter. So this is a structure called C-star algebra, and this is where this is our framework. So we'll define what's a C-star algebra. So a C-star algebra is an algebra over the field of complex numbers, which is also a Banach space, and it has a conjugate linear involution star. So involution is a map star which satisfies x star is equal to x. So this involution also satisfies, I mean this structure also satisfies the following, that norm of xy is less equal norm x times norm y, then star of xy is equal to y star x star, so it gets flipped, and the norm of x star x is equal to norm x square. So this last equation is called the C-star identity. I think Hriday covered this in this talk. And A is called unital if it has a multiplicative identity. So in this talk, all C-star algebras will be assumed to have a multiplicative identity. And the following are some examples of unital C-star algebras. So obviously the field of complex numbers itself. Then we have these matrix algebras. Then we have the infinite dimensional analog of them, which is B of H, of course. And we also have this space C of X, which is the space of complex valued continuous functions on a compact Hausdorff space X. And as you can notice, I have written this in a different color. So I want to distinguish this C of X from all these other algebras. So in a way, we will give some properties that these first three satisfy, but C of X won't satisfy. And in that sense, this C of X is in general a bad kind of C-star algebra. And before going further, let us define what is called the spectrum of an element. So the spectrum of an element X in a C-star algebra is the set of all scalars lambda such that X minus lambda times one is not infinite. And it is a non-empty compact subset of the complex plane, and it is denoted by this sigma of X. And the spectrum generalizes the notions of eigenvalues in the case of these matrix algebras, and also the range of continuous functions in the case of this C of X. And now here's some infodom about the properties of elements in a C-star algebra. So an element is said to be normal if x star x is equal to x star. So it commutes with its adjoint. So this x star is called the adjoint of x. And it's called self-adjoint, of course, if x is equal to its adjoint. And equivalently, it is equivalently, x is self-adjoint if only if it is normal and its spectrum lies in the real line. So you can think of these normal elements as analogues of complex numbers and self-adjoint elements as analogues of real numbers. And similarly, these positive elements you can think of as analogues of non-negative real numbers. So an element is said to be positive if x is equal to the square of some self-adjoint element, or if it's equal to this y star y for any element y in the C-star algebra, or if it's normal and its spectrum lies in the non-negative real. So all these three conditions are actually met. And we call it's a projection if it's self-adjoint and idempotent, and equivalently if it's normal and its spectrum is contained in the two elements at 0 and 1. It's called a unitary if x star x is equal to x star is equal to 1. Equivalently, if x is normal and its spectrum lies in the unit circle, then we'll call x an isometry if x star x is equal to 1, and we call it a partial isometry if x star x is a projection, or equivalently x star is a projection. So with that out of the way, okay, one final remark is that till this unitary, everything which we have defined is automatically normal, but in general, an isometry or a partial isometry is not normal. Any questions so far? Okay, so let's move on. So now we will define some properties of C-star algebra. So for the first property is the functional calculus. So we will denote this C of C we will denote it to be the star algebra of continuous complex valued functions on the complex space. And given any normal element of a C-star algebra, what we can do is define this in a nice way a star algebra homomorphism phi x from this C of C to A, which satisfies 1 goes to 1 and identity goes to x. And this homomorphism is called the continuous functional calculus. And for any continuous function f, we denote this its image phi x of f by f of x. And we can interpret this as evaluating the function f at the point x. And this evaluation depends only on how f acts when restricted to the spectrum sigma x of x. So now, as a sanity check, we can see that this 1 of x is equal to the constant 1, and identity of x is equal to x, which is what we expect to happen. Okay, so here are some examples of this continuous functional calculus in action. So in the case of matrix algebras, if x is a diagonal matrix, then f of x is just the matrix that replaces all entries lambda of x by f of lambda. And if A is the algebra C of x, then f of x is nothing but f component of x. This is the continuous functional calculus. So now we ask the question that can we extend the continuous functional calculus to a larger class? What we want to do is to define something called the Borel functional calculus, where this class of continuous functions is replaced by the class of Borel measurable functions. So we maybe like one of the motivations to do this is maybe we want to evaluate the characteristic function of an open set at some normal element, which is like restricting that element to that open set. I mean, it can be interpreted in that way. So
I had a question.
Yeah.
So in your previous slide, how do you define it for, like, if you have a diagonal operator, then you can define it. If it's not, how do you define it?
So what we can do is, so we can only do this for normal operators. So if it's x is normal, you can change the basis and make it diagonal. And then you do the same thing and again change back the basis. That is one of the ways to.
So this image will always lie in the normal.
Yeah, yeah, exactly.
Okay.
Yeah.
Okay, cool.
So, so this is, so we want to define this Borel functional calculus, where now we want to extend this to the class of measurable functions. And note that suppose this C-star algebra A admits the Borel functional calculus, then since like simple functions are dense in the space of any bounded subset of the complex plane, we get that the span of projections will be dense enough. And obviously this cannot happen when A is equal to C of x for some non-singleton finite points, because this C of x won't have any non-trivial projections. And so now what we want to do is we wish to find sufficient conditions only when this can be achieved. So this is one of our aims. Then another one is what we call polar decomposition. So given an x belonging to A, we can define this mod x to be the square root of x star x. So this is nothing but, so we have this function square root on the non-negative real line. We can just extend it in any way to the complex plane and then apply this functional continuous functional calculus to get this square root. Okay, so now what we have is this theorem of polar decomposition. So given any x in B of x, what the result that we have is that there exists a partial isometry U in B of x such that x can be written as U times mod x. So the natural question to ask is, can this happen for any C-star algebra? And the answer is no. So for example, again, let A be C of minus 1, 1, and x just denote the identity map T goes to T. Then mod x of T will be equal to mod T. And now if x is equal to U mod x, then U of T is supposed to be minus 1 if T is negative, and it's supposed to be 1 if T is positive. So this cannot happen for any continuous function. So we do not have polar decomposition in this C of minus 1. So again we ask that what condition should we impose on E such that we get this polar decomposition. And now the last property we want to explore is something called this order completeness. So it's perhaps like the most important property because this order completeness along with an extra technical condition will guarantee this existence of this Borel functional calculus as well as polar decomposition. So let's go to order completeness. So what we will do is we define an order on the self-adjoint elements of a C-star algebra. So recall that these are analogous to the real line. So given any self-adjoint x and y, we say x is less equal y if y minus x is positive. And this defines a partial order on this ASA that respects addition and multiplication by non-negative scalars. Okay, so we will now want to define and investigate the completeness of this order. So let us turn to the classical case of R to get an idea of how to do this. So okay, what is R actually? So R is the completion of the rational numbers, but we can do this in two different ways. So one is the Cauchy or metric completeness, which means that every Cauchy sequence has to be convergent. And the other is the so-called Dedekind or order completeness, which means that every non-empty subset of the real line which is bounded above has a least upper bound, which we will call an LUB. So C-star algebras are obviously metric complete because they are defined to be Banach spaces. But then we ask that what about order completeness? So we will need to define this order completeness. So a partially ordered set is said to have the strong LUB property if every non-empty subset that is bounded above has an LUB. So this is the same as the property R, and we say that it has the LUB property if every non-empty directed subset that is bounded above has an LUB. So if you recall, a directed subset is a subset in which given any two elements, there is a third element in that subset which is greater or equal to both of them. So obviously this second condition is weaker than the first condition, and we will be using this condition for reasons which will be clear later. So, but note that for a totally ordered set, these two conditions are equivalent. And now we call a C-star algebra order complete if the set of its self-adjoint elements has the LUB property. So again, the question is that is every C-star algebra order complete? So again, the answer is no. So again, we take this bad C-star algebra C of 0, 1. And so let S denote the set of all functions in C01, which is between this 0 and 1, and such that restricted to this interval 0 and half, this gives 0. So take this set of all such continuous functions. Then you can easily see that it's a directed subset of the PSA, which is bounded above by 1. But this set S fails to have an LUB. So the reason of this is that if x0 is the LUB of S, then x0 of t is 0 whenever t is strictly less than half, and x0 of t is 1 whenever t is strictly greater than half. And this cannot happen for a continuous function. So this second point, I'll leave it as an easy exercise, but you need to be careful that this LUB is not the pointwise LUB, but the LUB in this partially ordered set is. Okay. So we see that C-star algebras, though they are metric complete, they need not be ordered. But what we have is that this B of H is ordered complete, which means that the set of self-adjoint elements has the LUB property. But what about the strong LUB property? Because it's a natural question to ask because this is the more natural looking property, since there was no restriction on which subset would be. So we see that if x and y are these matrices, then this two element set x and y doesn't have an LUB. And so this strong LUB property is too strong a property to consider because we cannot distinguish these C-star algebras using this strong LUB property. And most likely there will be very few C-star algebras which satisfy this strong LUB property. So we will not be looking at this strong LUB property and just consider the LUB. So the question to ask is which C-star algebras are order complete. So this is like one of the main questions, and before answering this question, we will give some definitions on order complete C-star algebras. So first, for any C-star algebra A, we can define what is a positive linear functional on this C-star algebra. So it is a functional which takes any positive element of A to a non-negative real number. And what is very well known is that any positive linear functional is always bounded. So now we restrict to order complete C-star algebras and give some further definitions. So if A is order complete, we say that a positive linear functional is normal if for any directed subset S of this set of self-adjoint elements with LUB x0, we have that phi of x0 is the LUB of all phi x, where x varies over S. So this means that this phi respects this LUB structure. So such a linear functional is called normal, and keep this in mind because this will be a very important property. And the set of all normal positive linear functionals define a topology tau order. So order stands for order. So this topology is on A, and it is the smallest topology with respect to which all these functions are continuous. And with respect to this topology, this A is a locally convex topological vector space, but it may not be Hausdorff. So now we answer the condition that one needs to have, or which is sufficient to get everything that we want. So let's move on to something called W star algebras. So W star algebras are actually an abstract version of Neumann algebras. So like in manifolds, we can give an abstract definition of manifolds or give a concrete definition which is an embedding in some Rn. So similarly, we have this abstract notion of W star algebras, and von Neumann algebras will be there some suitable embeddings of them in V of H. So let us define these W star algebras. So a C-star algebra is called a W star algebra if it's isometrically isomorphic to the dual X star of some Banach space X. And such an X will be called a pre-dual of M. And this pre-dual defines a mixed-star topology on M, which a priori depends on which X we are choosing. So since Banach space can have multiple pre-duals. But the great part about this is that we have a mixed-star topology on M, and so the unit ball is compact with respect to this topology. So this is like a dream come true, and in norm topologies we only have this in finite dimensional spaces. So since we have a better topology, we get better things. That is the aim of these non-linear methods. And one of the things is that any W star algebra admits the Borel functional calculus, polar decomposition, and is order control. So these are the things which we want, and we get them by this condition which we impose. And now we will see that this mixed-star topology is actually independent of any X that we take because it is equal to this tau chord which we defined before. So this X is unique up to isometric isomorphism, and the mixed-star topology is canonical. So there is, on the W star algebra, there is only one topology to choose. And so we take this as the default topology on M unless otherwise specified. So maybe sometimes we might want more topologies, so we specify that. And the uniqueness of pre-dual means that any star algebra isomorphism between two W star algebras is continuous with respect to this topology. So we have a result like this for C-star algebras where any star algebra homomorphism is non-continuous. So in W star algebras we don't quite get that, but if the homomorphism is an isomorphism, then we still have this continuity. So we have the following relation between W star algebras and order complete C-star algebras. So an order complete C-star algebra is a W star algebra if and only if the topology tau word on it is Hausdorff. So this is the technical condition which I had mentioned, which gives us a great other property that we want. And equivalently, if any non-zero positive element or any non-zero positive element X of M, there is a normal positive linear functional phi on M, which maps this X to a strictly positive real number. So this is the biggest example of a W star algebra in some way. So B of H is a W star algebra. So it is isometrically isomorphic. The dual of the space of trace class operators on H, and we enclose this space with the trace norm. So this forms a Banach space, and its dual is isometrically isomorphic. So now we will define von Neumann algebras. So note that first of all that any weak star closed star subalgebra of a W star algebra is itself a W star algebra. And this is nothing special about the algebra structure. This holds for any dual of Banach space, of any Banach space. Okay. And we can achieve some sort of converse. So this is the celebrated theorem of Sakai. So this says that every W star algebra can be embedded. I mean, it is star algebra isomorphic to a weak star closed unital star subalgebra of H. And for those who know this, there is an analogous result in the theory of C-star algebras, which says that every C-star algebra is star algebra isomorphic to a non-closed star subalgebra. So instead of this non-closed, we get weak star closed. And okay, so this is the definition of a von Neumann algebra. It is a weak star closed unital star subalgebra of V of H. And hence, what this Sakai's theorem says is that every W star algebra is isomorphic to a von Neumann algebra. And by this first bullet point, we get that every von Neumann algebra, since V of H is a W star algebra, every von Neumann algebra is also a W star algebra. So in some way, these two notions are the same. But one needs to be careful because this W star algebra is an intrinsic property of the algebra, whereas a von Neumann algebra is a property of embedding also. And so we might have a star subalgebra of V of H, which is a W star algebra, but not a von Neumann algebra, because this W star algebra could be embedded in this V of H in the wrong way. So one needs to be careful about this. So now we know that any any W star algebra can be embedded in a nice way in this V of H, and so we can use the full force of whatever properties we have on V of H. So we will define these two topologies on V of H. So first is the so-called strong operator topology, which is the smallest topology, which for which these maps X goes to X continues to every vector psi. And this is the topology of pointwise convergence, as you can see. And this WOT is the smaller, which is the weak operator topology, is the smallest topology for which the maps of the form X goes to inner product of X xi with eta are continuous for all vectors xi. So we have these two topologies, and so now we have three topologies on V of X other than the norm topology, which are the SOT, WOT, and weak star topology. So we have the following relations. That WOT is coarser than both the SOT and the weak star topology. And the convex subset of V of H is SOT closed defined only if it is WOT closed. And on bounded subsets of V of H, the WOT and weak star topology coincide. So these are the relations between these three topologies. And now we will go to some fundamental approximation theorems. So without these theorems, you cannot move ahead in this field of von Neumann algebras. So the first is called the Kaplansky density theorem. So if we have a star, say if we have a star subalgebra of V of H, which need not be unital, then given any X in the SOT closure of A, there is a net in A that converges to X. So this is just the property of closure. But what we in fact have is that this net can be chosen such that if the norm of every element in the net is less or equal to the norm of X. So this is kind of great, but it's not true in general. And further, what we have is that if X is either self-adjoint or positive or unitary, then each element in this net can also be chosen to have the same property. So this is the Kaplansky density theorem. And for the next theorem, we will need to define what is called as commutant of a subset. So for any subset of V of H, its commutant is defined as all those elements in V of H which commute with every element in this subset. And one can note that yes, for any subset S, S is a subset of its double commutant. So double commutant is defined as the commutant of its commutant. And if S is a subset of T, then T commutant is a subset of S commutant. And combining these two results, we get that the triple commutant of S is the same as the commutant of S. And one can also notice that the commutant of S is a SOT closed unital subalgebra of V of H, but it need not be star closed. But from here we can see that if S is star closed, then the commutant will also be star closed. Okay, so let's come to this von Neumann double commutant theorem. So if we have a unital star subalgebra of V of H, which we will call M, then the following 5 properties are equivalent. So first property says that M is equal to its own double commutant. Second property says that M is the commutant of some star closed subset S, and the rest of the properties say that M is closed with respect to each of these 3 topologies. Okay, so we'll give a sketch of the easier parts of the proof. So one if and only if 2 is trivial by whatever we discussed on the previous slide. And since M is convex, and since convex sets are SOT closed if and only if they are WOT closed, we also get 3 if and only 4. So now 4 if implies 5 is trivial because the WOT is coarser than the mixture topology. And for the converse, what we will do is that we want to show that M is WOT closed. So we take any X in the WOT closure of M, and we get that there is a non-bounded net in M which converges to X in W in SOT by the Kaplansky density theorem, and the convergence will also happen in WOT because the WOT is coarser than the SOT. So we have a net bounded net converging to X, and since on bounded subsets this WOT coincides with the weak star topology, we also get that this bounded net converges to X in the weak star topology. And since M is a weak star closed, we get that X belongs to M, and hence M will also be WOT closed. And we also, since the commutant of any subset is SOT closed, we also get that this 1 implies 3 is trivial. The converse is slightly difficult, so we will not get into that. So these two are like the most basic and fundamental theorems about algebras. And having done with this basic theory, we will move on to examples of algebras. So first we see abelian non-Neumann algebras. So suppose we have a probability space omega A mu, then L infinity mu is a C star algebra, and it is also a W star algebra because it has the dual L. And L infinity mu can be naturally embedded in this B of L to mu as a von Neumann subalgebra via the map x goes to mx, where mx is the multiplication operator. So it is defined by mx of n is x into f. And we can do the same thing for little L infinity of s for any set s. Second is group von Neumann algebra. So these are the first kind of non-trivial examples of von Neumann algebra which we see. So let G be a countable group, and we see look at its left regular representation. So this is the representation from G to B into G, which sends this S to lambda S, where this lambda S is defined by lambda S of delta T equal to delta S. So this delta T is the indicator function of this small t. And all these indicator functions form an orthonormal basis of L to G. So what we see is that this lambda S actually permutes this orthonormal basis, and hence this lambda S is a unitary term. And we define this group von Neumann algebra LG to be the double commutant of this set of lambda S's, where S varies over G. Now we can see that if G is abelian, then this L of G is also abelian. And so one might wonder whether it also is of this form L infinity. So in fact it will be, and when G is abelian, then L of G is isomorphic to this L infinity of the R measure on G hat, where G hat is the dual group of G. So we have seen the examples and basic definitions. So any questions so far?
Chinmay, I have the question. Is this map lambda is sort of convolution?
Lambda is sort of, yeah, I think, right. I mean, this delta t is in L2G, but yeah, if we take things in L1G, both things in L1G, then yeah, you can think of it as good.
Okay. Thanks.
Okay. So, Yeah, so let's move on. So as we saw that for a W-star algebra, we have this Borel functional calculus, and we saw that because of this Borel functional calculus, we get that the span of projections is non-dense in the algebra. So von Neumann algebra therefore has a lot of projections in it, and so it's worthwhile to study these projections themselves. So we move on to the so-called theory of projections. So let us first of all recall what are these partial isometries. So a linear map from H to K is called a partial isometry if U restricted to its kernel perp is an isometry. So a partial isometry can be thought of as a unitary when you restrict the domain and codomain to its kernel perp and the range respectively. And we see that this U star U and UU star are projections. So this U star U is projection onto this kernel perp of U, and UU star is a projection onto range of U. So this kernel perp of U is called the initial space, and the range U is called the final space of U. So this partial isometry can be seen as being a unitary between the initial and final space, and outside it's zero. Outside the initial space it is zero. And what we can see is that this U star will also be a partial isometry, such that the range space and final spaces are flipped. That's what. And these partial isometries can in some sense measure the size of subspaces. So that means if H1 and K1 are closed subspaces of this H and K respectively, then we get that this dimension H1 is less equal dimension K1 if and only if there is a partial isometry with initial space H1 and final space contained in K1. So these partial isometries can be thought of as injective functions between sets, and these subspaces or the projections onto them can be thought of as sets. So this is like the model which we want to use. Okay. So we now define what is called the Murray-von Neumann equivalence of projections. So first of all, one remark to note is that if P and Q are projections, then P is less equal Q. So this less equal is in the sense of C star algebra, which means Q minus P is positive. If and only if the range of P is contained in range Q. So you can also think of as a smaller projection is less than or equal to a bigger projection. Okay. So now we'll define this Murray-von Neumann equivalence. So let P and Q be projections in M. We say that P is Murray-von Neumann less equal to Q if there is a partial isometry U in M with initial space or projection onto initial space P and final space is contained in range Q. So this is like this third point. We are trying to do something like the third point with the added caveat that this partial isometry should come from the von Neumann algebra M itself. And so we have that. So the initial space U star U has to be P and U star is less equal to Q. And we say that they are Murray-von Neumann equivalent if there is a partial isometry U such that initial space is range P and final space is range Q. And so this Murray-von Neumann is equal to difference of pre-order on the set Pn of projections, and this equivalence defines an equivalence relation. And so these we will interpret again this P and Q as sets, and this U's as functions between the objective functions. So if their initial space is P. And we have a Schroeder-Bernstein theorem kind of result here. So it says that if P is less equal to Murray-von Neumann less equal to Q and Q is Murray-von Neumann less equal to P, then we in fact have Murray-von Neumann equivalence with P and Q. So we have this new structure on projections which depends on this von Neumann algebra because of this added condition, the restriction that you should belong to. Okay. So now since we are interpreting these P and Q as sets, we will try to define what are finite and infinite projections. So recall that the set is infinite if and only if it's in bijection with a proper subset of itself. So similarly, we will call a projection infinite if it's Array von Neumann equivalent to some proper subprojection Q which is strictly less than P. And otherwise we will call it a finite projection. And the von Neumann algebra M itself will be called finite or infinite according to whether this biggest largest projection 1 is finite or infinite. And now let us define the center of a von Neumann algebra. So the center is just a set of all elements in M which commute with every element in M. And the central support of any projection is defined as the smallest projection now in the center whose range contains the range of P. And now we define this finite and infinite projections, and now we define something called a properly infinite projection. So P is called properly infinite if for any central projection P we have E into P is either 0 or infinite. So note that for the product of any two projections need not be a projection, but if they commute then it will be a projection. So this EP is indeed a projection, and we can talk about whether it's finite. So this is the definition of a properly infinite projection. And now we will go to some what is called as type decomposition. So we will define some types of von Neumann algebras. So let M be a von Neumann algebra, and let P be a projection in M, and P dash be a projection in this commutant of M. So note that commutant of M is also a von Neumann algebra. Then we have that this PMP and P dash M are both W star algebras, and they can be naturally viewed as von Neumann subalgebras of the bounded linear functionals on P of PH and P dash H respectively. And this PMP is a star subalgebra of M, whereas P dash M is a quotient of M. And using these, we define what is called an abelian projection. So projection P in M is called an abelian if the this is called the cut down of M with respect to P. So if this cut down is abelian, then P is called an abelian projection. And now we divide these von Neumann algebras into types. So von Neumann algebra is said to be type 1 if there is an abelian projection in M with central support 1. Then it is called type 2 if M has no non-zero abelian projections, but there exists a finite projection with central support 1. And it's called type 3 if M has no non-zero finite projections at all. And you can see that these definitions are weird, and so it's not clear why M should be one of these types. So indeed it's true that M need not be any of this type. But what we have is this so-called type decomposition. So that means that you can decompose M in uniquely algebras of this type. So the theorem says that there exist unique central projections in M which add up to 1, and such that E1M is type 1, E2M is type 2, and E3M is type 3. So this M can be written as a direct sum of all these three. So M can be decomposed into these algebras of different types, and this decomposition is unique. And so these type 3 algebras are very difficult to study since there are no finite projections in them. But this type 1 and type 2 projections or algebras can be decomposed further. So if M is a type 1 von Neumann algebra and n is any cardinal number, then we say that M is type IN, so it's called type IN instead of 1n for some reason. But it's called type IN if there is an orthogonal family PI of abelian projections in M such that they add up to 1, and the size of this indexing set is equal to M. And M is said to be type, so if M is of type 2, then it is said to be of type 2-1 if the identity projection is finite, and it's said to be of type 2 infinity if the identity projection is properly infinite. And similarly, we can divide type 3 projections also in further parts, but that is very difficult to do, so we will be able to do that. But now we have this further type decomposition. So if M is of type 1, then there is a unique set of cardinal numbers which we denote by script n, and a unique orthogonal family En, which is indexed by the script n, of non-zero projections in the sector, which add up to 1, and such that this ENM is type In for every in this sector. And so can again decompose this M into a direct sum of these type In algebras, and this also can be done uniquely. And similarly, if M is type 2, then there exist projections P1 and P infinity. These also are unique in the sector such that they add up to 1, and even M is type 2 1 and E infinity M is type 2 infinity. So we can do this kind of decomposition also. And now so this is, we are done with this type decomposition. So now we will also define what are some special kinds of non-even algebras called factors. So M is called a factor if its center is trivial, that is, the center consists only of these scalar multiples of 1. And we in general we have this type decomposition, but the nice thing about factors is that we don't need to do this type decomposition. Any factor is actually of exactly one of these types. So a factor is either of type In or some cardinal number n, or it is of type 2 1 or type 2 infinity or type 2. So there is no decomposition needs to be done. And we have this Murray von Neumann pre-order on n. So if m is a factor, the nice thing is that this pre-order is total. That is, either p is less equal q or q is less equal p for any p and q in projections. And what we can have is that this m can be decomposed into a direct integral of factors. So we won't define what are direct integrals here, but this is another. From this you can see that these factors are sort of building blocks of von Neumann algebras, and so they are very important to study. Okay, so now let's see the examples of these factors. So factor is said to be of type In. Sorry, the only factor of type In is B of L2S for a set S which has n elements. So there can be no other factor of type In. And if n is finite, then obviously this factor is the matrix algebra element. And for a countable group G, the group von Neumann algebra which we defined before is a factor if and only G is ICC. So ICC stands for infinite conjugacy classes. So that means that every non-trivial conjugacy class of G has to be infinite. And when this happens, then LG is always a type 2-1 factor. So these are the factors. And now finally we will see a class of von Neumann algebras called the tracial von Neumann algebras. And we'll see them because their theory is sort of easier than the general von Neumann algebra and also interesting. So first of all, we'll give some definitions. So von Neumann algebra is so let's start with the sister algebra A, and a positive linear function on A is called faithful if for any positive element x, phi of x is 0 implies x is 0. So any non-zero positive element goes to a strictly positive real number. And this functional is called tracial if phi of xy is equal to phi of y for all x and y. And von Neumann algebra M is called countably decomposable if it does not have any uncountable orthogonal family of projections in M. Okay. So we will define what is a tracial von Neumann algebra. So M is called a tracial von Neumann algebra if it admits a faithful normal trace. So that is a tau from M to C which satisfies this tracial property, and it's positive and also normal, which we had defined earlier, that it respects this immutable. And we see by this tracial property that since tau of u u star u is equal to tau u star for every partial isometry. And so we get that for any Murray von Neumann equivalent projections P and Q, we get that tau of P is equal to tau of Q. And hence, if we have a proper subprojection P of Q, the faithfulness of this tau implies that tau of P is strictly less than tau of Q. So this P and Q cannot be Murray von Neumann equivalent. So every projection in M has to be finite, and so this linear Fisher von Neumann algebra is finite. And the faithfulness and normality of this tau also implies that any Fisher von Neumann algebra is countably decomposable. Because if tau of Pi is non-zero for every Pi, then the normality will imply that the tau applied to the addition of all these Pi is infinite. So we also get any Fisher von Neumann algebra is countably decomposable, and conversely, any finite and countably decomposable von Neumann algebra is trivial. So the proof of this is quite involved, and so we will go through it here. Okay, so now let's see what is the nice thing about Fisher von Neumann algebras, and for that we'll need to see a couple of technical results. So first result is about C-star algebras, and it's called the GNS construction. So it says that if phi is a positive linear functional of A, then we get a unique triple. So an inward space H, a projection phi from A to B of H, and a vector xi in H which satisfies these two properties. First of all, that this phi of A xi is span of this phi of A xi set is dense in H. So this xi is kind of the cyclic vector for this projection phi. And the second property is that this phi of x is defined by this new product phi x xi with xi. So this is called the GNS construction of this linear function phi. And we have this following property, that if A is a von Neumann algebra, then this linear function is normal if and only if this projection, if and only if this pi is normal. So by normal here we mean it's continuous with respect to the weak-star topology. And we get that this phi x xi is non-zero for all x if and only phi is faithful. So in particular, phi being faithful implies that this representation phi is also faithful. Okay. And another result that we will need is that if M is a subset of B of H, it's a von Neumann algebra, and we have a Spinettel's and normal star algebra from M into some other B of K, then the image is also von Neumann algebra. And the main thing to note is that if this phi is injected, then this phi m is also M and phi m are both W star algebra, and this phi is an isomorphism between them, and so it's also a continuous isomorphism. So therefore, this M can be identified with phi of M if this phi is injected. Okay. So now we in Fisher von Neumann algebra we have this faithful normal trace, and we will now look at this GNS representation. So the GNS triple will denote by the GNS space will be denoted by A2M, and let phi be the representation, and let this cyclic vector which we have be called omega, capital Omega. Okay. So now this phi of M is a von Neumann algebra because this tau is normal, and its phi of M is phi is faithful because this tau is faithful, and so this M and phi of M are isomorphic to each other, and so we will identify this M with phi of M, and so we can say that this M is actually a von Neumann subalgebra of this B of A to M, and we will see that this is a particularly nice embedding. So irrespective of where we start, which B of H M is a subset of, this is the embedding to look for, the embedding M inside B of H2. And we will also assume that tau of 1 is 1. We can do this by suitably scaling tau. Okay, so now here are a couple of things to do. So given any x, we get that this x norm of x omega by this simple equation, we see that it has to be the norm of x star omega. And so this map J, which is defined on m omega to m omega by gx omega is x star omega, since we have this equality, this map will extend to a conjugate linear unitary of whole of L2M. Because by the GNS property, this M omega is dense in this L2M. And what we get is that this algebra JMG, which is just the algebra JXJ where X varies over N, this is also a von Neumann algebra inside B of L2M. And we see that this J y star J, by simple calculation, we see that it acts on this vector Z omega, then we get Z y omega. So this is like multiplying this y on the right. So hence this element J y star J is denoted by R y, where R stands for y. So note that this J y star J commutes with X for any for all X and Y in N. This is because J y star J is sort of the right multiplication and X is gets multiplied on the left. So their actions do not interfere with each other and so they commute. And so we get that this JMJ is contained in N commutant. But what is actually the beautiful thing about this GNS space is that this JMJ is equal to N commutant. So in general, if we have such a conjugate linear unitary J, so not in the way which we defined right now, if we have any conjugate linear unitary J satisfying JMJ is equal to N commutant, then we say that this embedding of M is in the standard form. And so the nice result is that every W star algebra is isomorphic to a von Neumann algebra in standard form. But the proof is very difficult in the general case and it requires some specialized theory called modular theory. And so we won't go into the general case here. But what we will prove is that we'll prove this theorem, and that will show that the embedding of M inside this GNS space is in the standard form. So before going to the proof, we will see some examples of this standard form. So if M is equal to the L infinity of mu for some probability space, then by this this tau of x defined by integration is a faithful normal trace on M. And the GNS space is given by just this L2n, L2 of mu, omega is equal to 1, and this J map is given by F maps to F1. And further, this GMJ is actually equal to M. So M is its whole component in this case. And if M is the group von Neumann algebra, which is given by these left regular representations, we can define a trace on the group von Neumann algebra by tau of x is the inner product x delta E with delta E. And this will become a faithful normal trace. And by the uniqueness of the GNS space, we get that the GNS space of this trace is actually equal to this L2G itself. And so this means that this M was already defined to be in the standard form. And this omega will just be this delta E, the characteristic function of E. So E here is the identity element of E. And this J will be defined as J acting on delta S is equal to delta S inverse. And this J lambda S J, so where this lambda S is the image of S under the regular representation, will be rho of S, which is sort of multiplication on the right. So this rho S of delta T is defined as delta of Ts inverse. So we give this S inverse to show that this rho becomes a group homomorphism between G to B of E. And we get that this J and Gj is R of G, the so-called right von Neumann algebra. So this L of G is stood for left von Neumann algebra, and this is the right loop von Neumann algebra, which will just be the double commutant of all these rows. So these are the examples, and now we will just quickly go through the proof of this theorem and then we will. So for this we will use two lemmas. So first lemma says that if this T is in the commutant of J and J, then we have, so now consider this vector T omega, and since this M omega is dense in L2M, we get some sequence x in omega converging to T omega. So take this x in omega to be any such sequence. then what we get is that xn star omega converges to p star omega. So to see this, note first of all that this xn star omega is jxn omega, and so it preserves the norms of these xn omegas. And since this xn omega converges to p omega, it is Cauchy, and so this corresponding xn star omega will also be Cauchy. And so it converges to some vector xi in L2. Now, using this simple calculation, which you can see, we get that the inner product of t star omega with any x omega will, after going through a series of steps, will finally be equal to this inner product of xi with x omega. And hence this xi will be equal to t star omega, and so xn star omega will converge to t star omega. And now we will see this second lemma. So second lemma says that this if we have t in GMJ commutant and t prime in M commutant, then this inner product t prime t of omega with omega is the same as inner product of t prime omega with omega. So this is just by this series of equations. So this is a typo. I need to add a limit here. But this series of equations we get using this first limit. So this xn star omega converges to t star omega by this first limit, and so this equation is correct, and we get this. And now using these two lemmas, particularly the second lemma, the proof of the theorem is very easy. So if t is in JMJ commutant and t dash is in M commutant, then for all x and y in M, we have t dash t x omega inner product with y omega. You can bring this y here, and since it commutes with t dash, it can come inside. So it is this. But now this y star tx is in M commutant, is in JMJ commutant again, and this t dash is in M commutant. So you can apply the previous lemma and flip these two. And again x commutes with this t dash, so it goes inside, and we get t dash x omega inner product y omega is equal to t dash t x omega inner product with y omega. And this shows that this t dash t is equal to t dash, and so M commutant and GMJ commutant commute with each other. So that means M commutant is a subset of GMJ commutant commutant. So this is the double commutant of GMJ, and it is equal to GMJ. So this shows M commutant is a subset of JMJ, and the fact that JMJ is a subset of M commutant was already shown here. So we got both inclusions, and hence the equality here. So we get that this GNS space is embedding of M into B of this GNS space is in standard form. So thank you. This ends the talk. If anyone has any questions.